Today we're going to be discussing and exploring finite geometric series. Okay, so recall that a series, what a series is really just a sum. Okay, so we say sum of a sequence. And another thing I'm going to say about this sum at least is this: we call it a partial sum. In this case, we call it a partial sum. The reason why is because we have some geometric sequence that is, maybe finite, maybe infinite, but at least maybe goes out to the nth term. Maybe it goes on forever and ever. What we want to do is we want to go find the sum of the first n terms. And we express it this way. We say capital S sub n, which really is kind of a fancy way of saying let's go add up the first however many terms of this sequence here that just happens to be geometric. Okay. So since geometric sequences, they have some common ratio that they're being multiplied by every time, and maybe of course start at some first term. Since they're so predictable like this, then we've noticed a pattern over time that we can generalize. It says if you want to find the sum of the first n terms, here's how you do it in general. So we say given some geometric thing that's multiplying by r every time here essentially, we say with a common ratio that is not 1. That is, we don't want some rule that says, or say start at 2 and then have this be your rule, because if you had a base of 1 it wouldn't change ever, okay? But we say the sum of the first n terms. You notice that I'm writing it here differently as well. We say that this is the sum starting at the first term and stopping at the nth term. So that's exactly what this says over here, the first to the nth term here of the rule. Okay, so this is nothing more than the rule right here. And the nice thing about having the rule is, of course, if you had the rule, you would know that your first term would be this, and you know that your common ratio, so common ratio would be that right there, and you have the number of terms that you're adding up as your n value, okay? But the important thing to remember here is this is the rule for summing up the first n terms of a geometric thing. So in terms of needs, let's go ahead and write this down here. What are the things I'm going to need to know to find the sum of the first n terms here? And of course, it looks like we need the first term. So we see A1, we need our first term. This is on our grocery list here. And then we say, okay, well, what else do I need? I need R. So we're going to need to know the ratio, okay, the common ratio. And last but not least, we're going to need to know n, which it represents the number of terms. So we say really number of terms summed, okay, or being summed in our series. So this is our grocery list right here. But if we have these things, we could go ahead and find the sum of the first n terms. So let's go ahead and take a look at what I've got written here. Now, I've written these specifically in sigma notation because it tends to throw people off, all right? But let's really talk about what this says. We say that this is the first term down here, first term, and this is the last, okay, term. We could say the nth term. I'm going to write that in here, the nth term. And then we say this is our rule, okay? So in terms of what it is that I know after looking at this, what we're really finding, and I'm going to abbreviate this now, is the sum of the first 12 terms, because we're adding the first through the 12th term of this sequence right here, for which we just don't have any of the terms written out. We just have the rule. But the nice thing about having the rule is this. Let's talk about our grocery list over here. We have A1 and R just due to the fact that we say A1 would be this 4 and then R would be this 0.3. Furthermore, we say, well, how many terms are we summing up here? Well, I want n to be 12 in this case, so we say n is 12. But the sum of the first 12 terms, or at least this sum right here, we would say would have to be equal to, now using my rule up here, we say it's our first term, A1. And this first term is being multiplied by this. Now I like to fill in the blanks. I'm a fill in the blanks kind of guy. But you'll notice our rule up here basically states that we're going to have our R values in these two spaces. So we say 0.3, try to write neatly here. We say 0.3, and then we say this 0.3 up top is being taken to the nth power, and we see that our n is 12, of course. So this thing right here, I got to tell you, man, if you wrote this on your paper, I have to give you some sort of credit, because obviously this is the sum. It's just that nobody speaks this way. So here's the thing that is unfortunate about arithmetic. Sorry, did I say arithmetic? Finite geometric series. You get some messy numbers, okay, essentially. But we're going to start by calculating everything on the top here. Now, we cannot take 1 minus 0.3 to the 12th. We need to take 0.3 to the 12th, and we're going to take that away from 1. So here's the order I'm going to do things in here. I'm going to take this 0.3, and I'm going to raise it to the 12th power, which is a very small number, very small. And I'm going to take 1 away from it, and then just call my answer the opposite of that. So here's the numerator. And what we get to do now, you notice I say we get to do this. We're going to take all of this numerator divided by 1 minus 0.3. Now, 1 minus 0.3, I could say divide by, in parentheses, 1 minus 0.3. Or I could say divide by 0.7, which is what that comes out to equal. And I say, well, okay, so here's what we've gotten so far. We've got this entire quotient. We need to take this all times a 4 now. So we say times 4. So just following the order of operations, really, and we get this, we get approximately 5.714-ish. So we get about 5.714-ish is the sum of the first 12 terms so long as they follow this scheme right here. Okay. So we're going to try this again. I just want to point some things out here, especially on this rule. We say, all right, well, we're adding up the first 7 terms. So again, our grocery list, what do we need? We need our first term, we need our common ratio, and we need to know the number of terms we're summing. So we say our first term up here. Now this is the interesting thing. This 2 is the base of the exponent. So the number out front, this is actually our A1, and A1 in this case is actually 1, you guys. So 1 out in front of this. We say our R is the 2, and we say the number of terms we're summing here are 7. We can see that this is the last term we're summing, first to the 7th term. Rule for summing a finite geometric sequence, or a series that is, that says let's use our first term, so A1, and in this case our A1 is just 1, so we get 1. Let's go ahead and plug this in here. We say 1. There we go. Times now this, of course, complicated expression. It's not that complicated. I just don't like evaluating it. So we have 2 as our R value. We're summing 7 terms here. So we say this is R to the 7th power here. And so when we evaluate this, we see that on top we would get 1 minus 2 to the 7th, which, by the way, 1 minus 128. And on bottom we get 1 minus 2, which is a negative 1. Okay. So we're getting all of this times 1 out here, which that 1's not really going to matter. So we end up with negative 127 over negative 1, which is 127, which I want to say, I mean, when you consider this, you had a sequence here that started with the first term of 1 and was doubling every time. So we say second term would be 2, third term would be, 4? 4, 8, 16, 32, and 64. Is this 7? We say 1, 2, 3, 4, 5, 6, 7. You add all these up, you're going to get 127, which is how we would use this rule to find a finite geometric sum. Cheers.